The question that I want to look at today is, does this particular series converge? Now, in order to understand what's going on in that series, let me write out the terms more explicitly. So the sum, as I goes from 1 to infinity, of negative 1 to the I plus 1 over I, when I is 1, this is negative 1 to the second power. So I have negative 1 squared over 1 plus negative 1 cubed over 2 plus negative 1 to the fourth over 3, and so on. Now, when I take negative 1 and I square it, I just get 1 back. So this is 1. Negative 1 cubed is negative 1 times negative 1 times negative 1. Those first two negative 1s just make 1, leaving a third negative 1. So that is minus 1 over 2. When I have negative 1 raised to an even power, it comes back to be plus 1. And so what happens with this series is that the sign in front of the terms keeps alternating back and forth between plus 1 and negative 1. Now, this series is very close to a series that we've already seen, the harmonic series. The harmonic series is 1 plus 1/2 plus 1/3 plus 1/4, and so on. And we've already seen that that adds up to infinity. In other words, the harmonic series diverges. Because in this series, the signs alternate back and forth between positive and negative, we call this an alternating series. And this series in particular is the alternating harmonic series. In general, we have an alternating series whenever the signs of successive terms in the series keep switching from positive to negative and back and forth and back and forth. We can make that formal by using the following definition. An alternating series sum as I goes from 1 to infinity of a sub I has, for all I, the product of a sub I and a sub I plus 1 less than or equal to 0. So even if some of these terms are 0, I'm going to consider them part of an alternating series. Now, alternating series are extraordinarily nice as far as determining whether or not they converge. Now remember, with the harmonic series, the value of the individual terms in the series, the limit of the terms was 0, but the sum of the series, the sum of all the terms, was not 0. More precisely, the limit as I goes to infinity of 1 over I equals 0, but the limit as n goes to infinity of the sum I goes from 1 to n of 1 over I equals infinity. So you have to be careful whether you're talking about the limit of the sequence or the series. Okay, so that's what happened with the harmonic series. What about the alternating harmonic series? Well, let's start looking at those partial sums. Remember, a partial sum, S sub n, is the sum as I goes from 1 to n of the a sub I term. So instead of trying to add up all of the terms, all of the infinite number of terms in the series, we're only adding up some finite number of terms in the series. Okay, so let's see what the partial sums for the alternating harmonic series look like. So I'm going to make a little table I'll put I, well, let's call it n, and s sub n here. The first partial sum is just the first term in the series 1. The second partial sum is the sum of the first two terms in the series, which is 1/2. The third partial sum is the sum of the first three terms in the series. 1 minus 1/2 plus 1/3 gives us 5/6. The fourth term, 1 minus 1/2 plus 1/3 minus 1/4. 5/6 is 10/12 minus 3/12 gives us 7/12. And so on. We could keep going over and over and over again. Now, because this is an alternating series, you can see that at the second partial sum, we subtracted something. So s sub 2 is less than s sub 1. So s sub 3 is greater than or equal to s sub 2. Finally, to get s sub 4, I subtracted something again. So s sub 4 is less than or equal to s sub 3. And so we get this pattern where the odd partial sums and the even partial sums keep going back and forth. Now, what's the difference between the first partial sum and the second partial sum? Well, I subtracted 1/2, but I only added back 1/3. This is an example, this alternating harmonic series, of a decreasing sequence. At least in absolute value. So what I mean by that is that if I look at the absolute value of a sub n, it's less than or equal to the absolute value of a sub n minus 1. For example, when n equals 3, a sub 3, which is 1/3, is less than or equal to a sub 2, which is 1/2. And you can see that this pattern, oh, got my absolute value signs. And you can see that that pattern continues. No matter how large or small I make n, it's always going to be true that a sub n is less than or equal to a sub n minus 1. But what that's going to do for us is, you see, in going from the first partial sum to the third partial sum, we subtracted something, 1/2, which we didn't quite make up for by adding 1/3. That's why we only brought back to 5/6, which is smaller than 1. So when you have this decreasing sequence, you'll find that s sub 1 is greater than or equal to s sub 3, greater than or equal to s sub 5, and so on down the line. And that's what's happening with the odd partial sums. What's happening with the even partial sums? Well, in going from s sub 2 to s sub 4, we added 1/3, but we only subtracted 1/4. That makes s sub 2 less than or equal to s sub 4. And s sub 4 is less than or equal to s sub 6, which is less than or equal to s sub 8. So what we find is that the odd partial sums are going down, and the even partial sums are going up. So they look kind of like this. The odd ones, 1, 3, 5, 7, are coming down. The even partial sums, 2, 4, 6, etc., are coming up. Now, of course, we're interested in whether or not the partial sums have a limit. Are the partial sums converging to some number? Well, if the partial sums converge to a number, it's because the difference between the height of these odd partial sums and these even partial sums is converging to 0. But let's look at what the difference between those partial sums actually is. The nth term of the partial sum, minus the n plus first term is the sum of the first n terms in the series minus the sum of the first n minus 1 terms in the series. Now, almost all of those things cancel. In fact, the only thing that doesn't cancel is the a sub n term. So the difference between these upper odd partial sums and these lower even partial sums is the value of the sequence at the point n. Therefore, what's going on is the limit as n goes to infinity of s sub n exists if and only if the limit as n goes to infinity of the terms of the sequence equals 0. Now that's a really cool thing because that allows us to find convergence of alternating sums very, very easily. All we have to do for an alternating sum is check to see what the limit of the sequence is as n goes to infinity. Let me give you another example. Does the following sequence converge? The sum as I goes from 1 to infinity of natural log of I divided by I times negative 1 to the I power. Now, when you're looking for an alternating series, you should look for things like negative 1 to the I power or negative 1 to the I plus 1 power. Those sorts of things indicate that you're working with an alternating series. And what we need to know is what is the limit as I goes to infinity of the natural log of I divided by I. Now, in fact, I could include the negative 1 to the I here, but if this part is going to 0, this part isn't going to make any difference. So we can actually ignore it and put absolute value signs here so that we don't have to worry about the alternating sign. Okay, now we could use L'Hopital's rule in order to find this limit, but there's a rule of thumb that's much faster and much easier to use. And that rule of thumb is as follows. Logarithms grow more slowly than polynomials, grow more slowly than exponentials, grow more slowly than factorials. So what do I mean by this statement? Well, this is an example of a logarithmic function, the natural log. This is an example of a polynomial, I raised to the first power. This rule of thumb tells us polynomials grow much, much faster than logarithms. So because I've got something that's faster growing in the denominator than what's in the numerator, this limit is going to equal 0. Now, if you don't like the rule of thumb, go ahead and use L'Hopital's rule. There's no reason not to do things above board. But once you get this idea, it can make taking these limits much, much faster. Okay, so because the polynomial, the I to the power, grows much faster than the logarithmic power, that tells us that this limit is 0. And so the question, which I didn't completely write down, does this series converge? The answer is yes. When we use this test to determine if the series is converging for an alternating series, when we look at the limit as I goes to infinity of the terms of that series, we call that the alternating series test. So yes, by the alternating series test. Okay, so what exactly is the alternating series test? Let me write it out for you now that we've seen it in action. Lemma. This is the alternating series test. This says that if the absolute value of a sub n is less than or equal to the absolute value of a sub n minus 1, and a sub n times a sub n minus 1 is less than or equal to 0 for all n, then the sum as I goes from 1 to infinity of a sub n converges if and only if the limit as I goes to infinity of the absolute value of a sub I equals 0. So that is the alternating series test. And what it gives us is a quick way of determining whether or not a series converges. Let's see another example. So first, let me just be absolutely clear. The answer to the question of the day is yes, by the alternating series test. So the question of the day the answer is yes by the alternating series test. So let's ask a different question. Suppose we wanted to know, does 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, etc., converge? Now, this notation with the 2 exclamation point is what we call factorial notation. So let me just remind you, if you haven't seen these in a while, a factorial, n factorial, is n times n minus 1 times n minus 2 all the way down to 1. So if we're looking at something like 5 factorial, that's 5 times 4 times 3 times 2 times 1, or 120. Now, factorials, you'll notice, are the fastest growing thing in my list. So when I have a factorial in the denominator, that's going to be growing much faster than a lot of things in the numerator. So in this example, here, the limit as n goes to infinity of 1 over n factorial definitely equals 0. Because n factorial is going to infinity, and 1 is just a constant. So, yes, sum as I goes from 1 to infinity of 1 over I factorial times negative 1 to the I plus 1 converges by the alternating series test. But the nice thing about factorials is that they beat most other functions. They grow faster than polynomials. They grow faster than exponentials. So let's look at another example of that. Question. Does the sum as I goes from 1 to infinity of I to the 5th power over I factorial times negative 1 to the I converge? So now, this is an alternating series, and so what we need to know is what is the limit as I goes to infinity of I to the 5th power over I factorial. Well, I to the 5th is an example of a polynomial, and polynomials grow more slowly than exponentials and more slowly than factorials. So in fact, this limit is 0. So the answer is yes by the alternating series test. One more example. Suppose that we want to know does the sum, as I goes from 3 to infinity, of I factorial divided by e to the 3i times -1 to the I plus 1 converge? Now first I want to remind you, whether or not I start at 3 or 1 or 1,000 doesn't matter when it comes to determining if a series converges or not. Starting at 3 is the same as starting at 1. Now the second thing that I want to point out is that in the numerator we have a factorial. In the denominator we have an exponential. And in fact, factorials beat exponentials. So if I look at the limit as I goes to infinity of I factorial over e to the 3i, that is going to be infinity. It's not going to be 0 because factorials grow more quickly than exponentials. And so the answer is no by the alternating series test. So that is alternating series in a nutshell. If you've got a series where the terms sooner or later start decreasing in absolute value, then all you have to do is look at the limit of those terms as n goes to infinity, and if that's 0, the series converges. If it's not 0, the series diverges. That simple. Thanks for watching.